Most people believe bridges fail at the end of their lives, after years of traffic, after corrosion, after neglect. But some of the most disturbing bridge failures in history didn't happen after decades. They happened before opening day. No traffic crossed them. No commuters depended on them. No public warning signs existed. From the outside, everything looked normal. Construction schedules were active. Engineers were present. Progress reports looked reassuring. And then, suddenly, the structure was gone. Different countries, different bridge types, different engineering teams. Same outcome. That alone should make you uncomfortable. Because a failure can happen before use, then age, traffic, and where aren't the real danger. So here's the question almost nobody asks. Why do bridges collapse most often when they're not even finished? Pause. Most people assume construction is the safest phase. After all, everything is new. Nothing has been stressed for long. But that assumption is wrong. In reality, construction is the most unstable moment in a bridge's life. Not because engineers don't know what they're doing, but because the structure exists in a dangerous in-between state. Not raw materials anymore. Not a complete system yet. A structure in transition. And transitions are where systems fail. If you want to understand why failures happen, not just watch them, subscribe. This channel breaks down the hidden mechanics behind collapse. We haven't named a single bridge yet, and that's intentional, because once you see the pattern, the names almost stop matching. There's one belief that quietly sits behind nearly every construction stage failure. If a bridge meets code, it's safe. That idea feels solid, comforting, professional. Codes are written by experts, reviewed by committees, enforced by regulators. Engineers trust them. Contractors build around them. Governments approve projects based on them. So when people hear it met code, they mentally close the case. But here's the problem. Codes are written for finished structures. They describe how a bridge should behave after construction is complete, after all components are in place, after loads flow exactly as intended. Before that moment, the bridge exists in a completely different reality. During construction, a bridge is not truly a bridge. It is a temporary, evolving system. Load paths are incomplete. Critical elements may be missing. Temporary supports carry real forces. Some components are overstressed, simply because they are the only ones available. Forces don't flow as designed, because the design hasn't fully materialized yet. And yet, we treat these structures as if they are already whole. Schedules tighten, assumptions harden. Confidence grows prematurely. Failure doesn't care about drawings. It cares about current conditions. This is where danger hides. Codes protect final performance. But collapse doesn't wait for completion. Bridges don't fail as finished ideas. They fail as unfinished systems. And that misunderstanding sets the stage for everything that follows. Now, let's talk about what happens when a bridge fails while being built. No traffic, no public use, no final loading. Yet collapse still occurs. One of the clearest examples is the Curajara Bridge in Colombia. It was modern, large-scale, still under construction. From the outside, it looked stable. Then one major structural element lost capacity. Not explosively, not dramatically, quietly. And once that happened, the structure had nowhere else to send the forces. There was no alternate load path, no redundancy waiting to engage. The failure wasn't caused by final loads. It was caused by construction stage forces. Temporary load paths carried stresses they were never designed for. Incomplete systems behaved unpredictably. Erection sequences were underestimated. This is the part most people miss. The final design wasn't weak. The process was. A bridge can be strong when finished, and fragile while being assembled. Construction sequence matters. Order matters. Temporary conditions matter. Ignoring them turns safe designs into unstable systems. And this isn't rare. You see the same pattern across continents. Different engineers, different materials, same blind spot. Now consider a different scenario. A bridge that already exists, not abandoned, not obsolete, just being repaired. This is where people feel safest, because if the bridge has stood for years, surely it can survive maintenance. That assumption is dangerous. Repairs change the system. A clear example is the de la Concorde overpass in Canada. Work was ongoing above. Traffic continued below. Everything looked routine. Then a concrete slab began losing shear capacity. No dramatic warning. No sudden alarm. Just a gradual loss of strength, until gravity took control. Here's what mattered. The repair process removed more capacity than engineers accounted for. Temporary conditions erased permanent safety margins. The bridge didn't fail under service loads. It failed between states, neither fully intact nor fully supported. This in-between condition concentrates risk, and it's often overlooked, not because of negligence, but because transition feels temporary. But physics doesn't respect temporary thinking. Once you see the pattern, you can't unsee it. Construction stage is ignored. Temporary conditions underchecked. Schedule pressure overriding caution. Confidence built on the belief that nothing has failed yet. You see this pattern across decades, across bridge types, across countries. It appeared again in the Florida International University pedestrian bridge failure. Different design. Same assumption. So who missed it? The designer? The contractor? The reviewer? The regulator? The uncomfortable truth is this. Everyone assumed someone else checked the transition phase. Design focused on final performance. Construction focused on speed. Review focused on compliance. The most dangerous phase fell through the cracks. Bridges don't fail because engineers lack intelligence. They fail because transitional risk is underestimated. So when you hear about a bridge collapsing before opening day, remember, it wasn't random. It wasn't mysterious. It followed a pattern. That's why bridges are most likely to collapse before opening day, because engineers miss this. Subscribe if you want explanations that go deeper than headlines. Share this, because understanding failure early prevents it later.